Okay, let's unpack this. We're diving into, well, a really practical and kind of fascinating intersection today.
Yeah, it's where abstract math, specifically calculus,
Right.
meets the very real world of agriculture,
Yeah.
keeping plants alive.
Exactly. You send over some sources looking at how math concepts like differentiation integration can be made, more relatable for college students,
Hmm.
particularly in this context. So our mission here is to pull out the key stuff about using integration, specifically to understand something vital for farming.
Evapotranspiration.
Evapotranspiration, yeah, and how it affects crop hydration.
That's right. The sources really highlighted this example. It's a powerful way to show that calculus isn't just theory on a page.
So what is evapotranspiration exactly?
It's essentially the process of water moving from the ground and also from the plants themselves up into the atmosphere.
Okay.
It's really two things combined: evaporation, from the soil surface, and transpiration.
Transpiration, that's the plant sort of, breathing out water vapor.
Exactly, through their leaves. So think of evapotranspiration as like the total water loss from a field or a crop area.
Water loss from the ground and the plants.
Okay. And why is knowing that specific amount, that total loss, so important if you're, say, a farmer?
Well, because effective irrigation, as one source pointed out, it's all about replacing the water that's been lost.
Makes sense.
If you don't know how much water has actually left the system through this evapotranspiration, well, you're basically just guessing how much water to add back.
And guessing can be bad. Too little, the plants get stressed.
Right, and too much water. You waste it, obviously, but you also waste nutrients, energy. You can even harm the crop itself.
Okay. So knowing that total loss allows for what? Precise watering?
Precise irrigation scheduling, yeah.
Yeah.
You know what needs replacing.
Got it. Now, here's where it gets interesting for the math part, because that water loss, it doesn't just happen at one steady rate, does it?
No, definitely not. It fluctuates a lot.
Yeah.
Throughout the day with changing weather. Right. One source mentioned things like temperature, wind speed, humidity.
Yeah.
They all make the rate vary quite a bit.
Exactly. And what's really key here and fascinating is that you don't just need to know the rate of water loss at like one specific moment, how fast water is leaving right now.
Okay.
To actually manage irrigation over a whole day or a week, you need the total amount, the total volume of water that's been lost during that entire time.
Okay. And that's the connection. That's where integration comes in.
That's precisely it. Integration is the mathematical tool that's, designed exactly for this.
Yeah.
Summing up a quantity that's changing over an interval.
Like summing up the water loss rate over the interval of a day.
Exactly.
Yeah.
You integrate the rate of evapotranspiration over a period of time, and the result is the total water lost during that time.
How does that work, sort of conceptually?
Well, one source explained it nicely. Think of accumulating tiny slices of water loss happening each minute or maybe each hour. Integration's like adding up all those tiny, tiny slices. When you integrate, you get the cumulative volume, the total amount of water that's evaporated and transpired over that whole period.
So without integration, you'd just know how fast it's happening now, but not the grand total.
Which isn't very useful for deciding how much water to add back later.
Yeah.
Right. Integration transforms that rate data, how fast, into total volume, how much.
That seems like the crucial step for actually using the information. The sources also mentioned how you get that rate data, something about lysimeters.
Yeah, lysimeters are eddy covariance systems. They're basically sophisticated instruments that can actually measure the movement, the flux of water vapor going from the land surface up into the atmosphere.
So they give you the rate measurements.
They give you the rate data, yes, which scientists and farmers need.
Sure.
Then integration provides the mathematical framework. It takes that raw rate data.
And turns it into the total volume lost.
Exactly, which directly tells you about your irrigation strategy. It makes complex environmental measurements into, actionable numbers for keeping crops healthy.
So bringing it back, what does this all mean, especially thinking about making math relatable, like the sources wanted?
Well, it's just a really powerful demonstration, I think, that these mathematical tools you learn, like integration, they aren't just stuck in textbooks solving abstract problems.
Right. They have real, vital applications.
Absolutely. Directly impacting critical things, like growing our food, managing water sustainably. This example shows calculus isn't just finding the area under some curve on a graph.
It's about calculating something incredibly real, like how much water a field of crops actually needs to, survive and thrive.
By measuring these complex natural processes like evapotranspiration, it really underscores the power of mathematical modeling.
Yeah, seeing calculus applied directly to something so tangible, keeping plants healthy, is pretty neat. It definitely makes you think. What other, maybe surprising real-world problems out there could be understood or maybe even solved using the math concepts you're learning? We're thinking about those connections hiding in plain sight.